So let's see here. First things first, notice that this is degree 3. This is what? Degree 4. Which means that as we look at step 1, we don't have to do long division, right? We can see that asymptotically, this thing is going to look like y equals to 0. The horizontal asymptote for x really far out, it's going to be y equal to 0. So that's nice. So we can jump straight into the completely factoring this. Completely factoring this, what's that look like? This factors as x plus 2, right, times x minus 2, and then we've got x minus 8 squared. So, all right. This time, let's see here. We've got this one has zeros, 0 at 0 and 2, right? This one is 0 at minus 2, 2, and 8. So this one's more annoying than the previous example because there's an overlap, right? We have 2 shared by both the numerator and the denominator as zeros. Okay? So in this case, it's useful to introduce what's called the reduced function. So see, what's the reduced function? Well, the reduced function here is x squared over x plus 2 times x minus 8 quantity squared. So this is equal to f reduced of x. And that's for, well, I mean, this, to be fussy, this step right here, going from here to here, that's for what? This is for x not equal to 2. All right. So the reduced function, it's defined for like all x. Well, that's not true. It's defined for more x than the original function. In particular, the original function, since we have the same order, see this? We have 2 is appearing once in the numerator and x minus 2 is appearing once in the denominator. That means we have a hole in the graph at 2. So there's a hole in the graph. You see this here, and this here, and they're both the same. Same order. Order 1, order 1. So we get hole in graph at x equals to 2. All right? That's what that tells us. And more than that, where is the hole? Actually at 2 comma, you plug 2 into the reduced function. And that will actually give you where the hole is. So the hole is going to be at 2 comma, what happens when you plug 2 into that formula? We get what? 4 over 4 times 2 plus 2 is 4, right? 2 minus 8 is minus 6, so we get 4 times minus 6 squared. So where's my hole? My hole's at 2 comma, oh, the 4's cancel, right? So 1/36. So there's where the hole in the graph is actually at. All right. We could have done that later. We don't technically need that until like when we make the graph. Okay, so if you forget to do this until later, it's not a big deal. You can always go back and do it when you get to the graphing part. Okay, so number line time. And I'm going to put it over there again because, you know, I want to make the graph under the number line. So it's a good practice to leave yourself room to make the graph right under your number line, because that way you're not trying to like look back and forth and make sure that you've got things lined up. It's just good practice to just line it up to start with, right? So then you have less, it helps you reduce errors. Like if I had made use of my number line properly in the last example, then I wouldn't have made that mistake, right? So the zeros are, there's one at minus 2. There's another one at 0. There's another one at 2. And then all the way out here at 8, let's see here, it's about here-ish, right? There's a 0 out there. Now I want to add pluses and minuses as appropriate. All right, so what do we got? If you plug in like, oh, I don't know, plug in 9 into this, and you can easily see that it's positive, right? So I'm going to start out positive over here. All right. I get to 8. What's the nature of 8? Where's 8 coming from? 8 is coming from this x minus 8 squared, right? So what does that tell me? What do we do there? We bounce, right? So it's going to, the sign stays plus. So stay plus. All right. Write as many pluses there as you want, but the sign does not flip at 8 because we've got that x minus 8 squared. How about at 2? What's the deal with 2? Well, 2 is coming from x minus 2, right? Again, there is 2 of them. See, there's 1 in the numerator, 1 in the denominator, so there's a total of 2. And so that means that we don't flip sign again. So we stay plus there. You start thinking about that, that makes sense because like our hole in the graph is at 2, 1/36. So that means that it's positive, and once you understand more what hole in the graph means, that'll make more sense to you. How about 0? Oh man, look at this. So it's 0, 0 is from this x squared, right? So we bounce again. But the nature of the bounce is quite different here than it was at 8, as we'll see. And then at 2, minus 2 rather, that's coming from this x plus 2, right? So that, you've got minuses. So let me just talk a little bit more before I write the graph. So this right here, well, eventually I find the color I want. So here, this guy is a vertical asymptote, right? X-intercept is 0. This is also an x-intercept. Wait a minute, no, this was what? Hole in graph, right? And what happens over here at 8? That's coming from 8 being in the 0 in the denominator. So this is again a vertical asymptote as we're graphing it. All right. So here we go. And what's my horizontal asymptote is y equal to 0. So eventually the graph is drifting into the x-axis. So I got a vertical asymptote at minus 2. Vertical asymptote over here at 8. All right. I have a x-intercept at the origin, right? And yeah, now I've got a hole in the graph here, which is kind of sort of like here-ish, right? I'll just put it here. That's not, I mean, to be fussy, that would be really close to the x-axis on my scaling. But I'm just going to put it there so you can see it better, okay? And then, so here it is. So we do like this, all right? And then we're positive over here. And then we bounce off the x-axis because it's a square, all right? And then you got to kind of drift over here, get to the hole in the graph, which is where the hole in the graph was, I said, at 2, 1/36, right? And then apparently we drift back up like this volcano here, and then we're positive again here, and then we drift back down to 0 like that. So these here, and sometimes I draw the arrows on the, like I don't insist that you draw them, and I don't insist that I draw them, these arrows all the time, but some people draw arrows to indicate that it goes on and on like that. But there you go, that's the graph. So what's going on here is, how do you want to think about the bouncing versus the crossing, right? So if we have a square unopposed in the denominator, you can think of it, my brother says it bounces off infinity. So he describes like a volcano as kind of like it's bouncing off infinity, right? Whereas this one, I think my brother would say this crosses through infinity because it's coming from the x plus 2, which is, you know, an odd power. I mean, bouncing off the x-axis is clear enough. Crossing the x-axis is clear enough, right? But there is something similar to observe about the asymptotes. If it's a squared term in the denominator, it gives you like a volcano, either that opens up or down. If it's a odd power in the denominator, unopposed, then it's going to give you one of these things where it's going to minus infinity one way and going to plus infinity the other. Something like that. But that's it. That's all there is to graphing a rational function. You just have to figure out where the zeros are and track through it. There is more to say about what are called oblique asymptotes, but I think we're out of time for today, so that'll have to wait till next time. Thanks, guys.